Now we're going to take a look at concepts called associativity and precedence. If that sounds scary, don't worry. I promise you've already seen this before. Suppose we're looking at an expression like 33 plus 4 times 5 minus 7, all divided by 2, minus 4. We learn rules such as BODMAS, brackets, order, division, multiplication, addition, subtraction, so that we know the order to perform operations in. That list right there expresses precedence. The first ones have what's called highest precedence. You do those before any of the others. The lower ones have lower precedence. You do those after you've done the first ones. But we also have rules about associativity. They say A plus B plus C is the same as A plus B plus C, or A times B times C is equal to A times B times C. It means when we write A plus B plus C plus D, we can bracket it in any way we want. Same for multiplication. We call operators like plus and times, where bracketing doesn't matter, fully associative. It seems trivial, but there are a bunch of cases where this doesn't apply, like with the dot product on vectors and subtraction. For example, A minus B all minus C is definitely not the same as A minus B minus C. In this case, we always work from the left, and so subtraction is left associative. Eventually, we'll see in Idris that function application also associates to the left. Similarly for division, A divided by B divided by C is not equal to A divided by B all divided by C. We don't see division as often as subtraction, but the convention is the same, left associativity. And powers, or orders, are different as well. Sometimes powers are written with a caret, and so A caret B is equal to A times by itself, B times. When we see A caret B caret C, we usually mean A to the power of B to the power of C. In this case, we want to bracket starting from the right, so A to the power of all of B to the power of C, and say orders are right associative. Later you see that the list cons operator in Idris is right associative. In type signatures, which we'll cover in later videos, A arrow B arrow C actually means A arrow all of B arrow C, and A arrow B arrow C is completely different, and so arrows are also right associative. All of this means we can take 33 plus 4 times 5 minus 7 all divided by 2 minus 4 and turn it into a syntax tree like the one above. There might be some choice, like 33 plus all of 4 times 5 minus 7, or all of 33 plus 4 times 5 minus 7. But we know it doesn't make a difference in this situation. But sometimes the difference is important. An extreme example of this is the phrase, "John saw the man on the mountain with a telescope." Who is on the mountain? John, the man, or both? Who has the telescope? John, the man, or the mountain? We can bracket the sentence in multiple ways to answer the questions raised by it. In the same way, arithmetic expressions also form a grammar of their own little language. The question is now, can we figure out what is the grammar of arithmetic expressions? Let's start with the easy bit, numbers. Numbers are just a bunch of zeros to nines strung together. We call 0, 1, 2, and on up to 9 digits. So we say a digit is 0 up to 9. Then a number is just one or more digits. So we can say a number is a digit on its own, or a digit followed by another digit, or 3 digits in a row, and so on. Numbers go on forever, and we don't want to spend the rest of this video writing it out. In the next video, we'll see that with recursion, we can say number is just a digit, or a digit followed by a number, or even a number followed by a digit, and it encapsulates precisely what we want. Pause and think about that for a second if you want, but don't worry if it confuses you. Now for the tricky part of the language, the operators plus, minus, times, and divide. I'll only do the one plus operator, because they're all basically the same. A symbol with a left part and a right part. And we could even express it like an operator op is just plus, times, minus, or divide. But to keep things concrete, I'll just use the plus symbol for now. And you should keep in the back of your mind that the plus could just as easily be any other symbol, and everything else still applies just the same. So we want to figure out what an arithmetic expression is. We know that a number is an arithmetic expression, and so we have this so far. An arithmetic expression is a number. But we also know we can add two numbers. So an arithmetic expression is a number or a number plus a number. But now we have two things. And so we have three more ways of combining the expressions we have so far. We can either add a number to the left of the bigger expression. We can add a number to the right of the bigger expression. Or we can add two of those big expressions together. And we could keep going on forever. There are now 5 expressions, but we can combine all of those in more ways. We might get some duplicates if we're not careful, but that doesn't really matter here. And remember, each number is an infinite combination of digits going on forever, so we really do have a lot of arithmetic expressions here. Add back in the fact that for each plus symbol, we could have chosen one of plus, minus, times, or divide. You can start to see how things get out of hand quickly. When we learn about recursion, we'll see that arithmetic expression is either a number or an arithmetic expression op, another arithmetic expression, is a good way of expressing this concisely using recursion. So I hope you realize by now that you've already seen grammars a lot more than you first realized in your everyday life. Programming language grammars aren't that different, and they're nothing to be scared of. Whenever you need to read or write a bit of code, you know you can always break it down into smaller bits using rules like the ones I show you in this video. As you get better and better at this, learning new languages becomes really easy. You just find the syntax reference and then look up what each bit of the syntax means. In other words, it's semantics.